Also, another question: do you have any stories wanted to share with us, like related to lasers?
Well, so I have various random experiences with how to cut things. You know, cutting up things. There are so many ways of doing that. And you know, when I was much younger, I had just manual tools, and I would, you know, just use like a manual milling machine, for example, or wood cutting. You know, wood cutting equipment to build. I build all kinds of tables and things.
Like saws
and drills and band saw, table saw, jointer, planer. You know, in the case of woodworking, or manual milling machines, not CNC, but just, you know, you dial and you watch the numbers, or you turn the dials, whatever. It's completely manual machining operations, which is very interesting. It really, I think everyone should do that to just gain familiarity with the materials. But a big problem with that is that if you spend 3 days making something and then you make a mistake, it's, well, now I have to spend another 3 days. You know, you have one of them, and if you want another one, you have to do it all over again. A crucial difference with something like a laser cutter is that you make a design, you put it's done, now you have the part. Oh, wait a minute, that's wrong. Okay, fine, I make a small change, I push the button again, boom, here's another one. And so you can, the cycle of design it, make it, test it, that might be 5 minutes or something.
You'll get a quick response.
Right, you get a very quick cycle. And that means, you know, when I'm designing little mechanical kits and things, I might do that 20 times. You know, just redesign the part, boom, 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 boom. In the course of a day, I can make 20 different designs. And each one is a little bit better and fits a little bit nicer. And I could, you know, make this curve better here, or this would fit easier this way. Just iterate it very, very quickly because of how fast the machine is. Because, you know, once I've made one part, if I want a second one, I just push the button again, and boom, there it is. You know, less than a minute later, maybe, if it's a small part. So that's a really, I think it's sort of a phase change. It's not just a little bit better. It's like, it's no longer
with time.
It's an iterative. It's more like software than building things, right? Software also has this characteristic that once you get it right, you can just push a button and now there's a million copies all over the world, right? Or whatever. You put it on a server and suddenly everybody can use it. It's not quite like that, but the difference between making a part by hand and you have only one part versus you spend the same amount of time, but now you have a design and you can push a button, and every time you push the button there's another one. That's a huge change in sort of how you relate to the making of things. And people talk about that with 3D printers all the time. But the problem is 3D printers take a day to make a part. You know, many hours, they're very slow. And the parts are terrible. They're ugly, rough, you know, things, whatever. I don't like 3D printers. The laser cutter makes beautiful, nice, clean, strong parts out of cheap materials, as long as they're flat. So then if you compare that to other ways of cutting materials, things like water jet or plasma cutters, or, you know, wire EDM machines, all of which have different advantages. You know, there's things you can do with those technologies that you can't do with a laser cutter. Like if you want to cut, you know, very thick steel and you don't have, you know, 100 kilowatt 3-phase power coming to your house, you can do that with a plasma table, but you can't do it with a laser cutter. But they also have very serious disadvantages. You know, the plasma cutters are incredibly dirty. There's smoke everywhere. I mean, it's really unpleasant to be around a plasma cutter like that working. Water jet's incredibly expensive, very messy, everything gets wet. Wire EDM is unbelievably slow and even more expensive, although amazing in what it can do. You know, they all have these sort of problems. And laser cutting, you know, fiber laser cutting of metal is sort of has the same kind of, almost the same kind of simplicity and cleanness I mean, nothing will match the CO2 laser cutting acrylic. That's just, you put it in there, boom, it's done. Just nothing that you do. You don't need any extra supplies. Just nothing could ever be that easy. The fiber laser may be a little bit more complicated, but still much cleaner, much more sort of pure, as it were. You have a design, and now the design exists in metal. That's much closer with the fiber lasers than with other ways of cutting metal. And that, you know, among other things, it means, you know, let's say you're trying to iterate the design, right? You want to make a part, see if it works, change it, make another part. If you're using, let's say, a plasma cutter, that means you have to go off to the other building where you keep the plasma cutter because it's so dirty you can't keep it near your computer. And you make the part, and now you have to take a chipping hammer or something, or a surface prep machine or something to try to break off all the little slag that is stuck on the part, and maybe you have to sand it because it's gotten wet and it's rusty, and it's just a mess. And then you can take it back to your nice clean area with your computer, and you can look at it and say, oh, that's not right. And then you go do the whole thing again. If you had a fiber laser machine, you could keep it much closer, it's cleaner, and it makes a part, and you take the part, and it's the part. It's not, you know, something that can eventually be turned into a useful part if you spend enough time cleaning it.
Yes, considering the cleanliness.
Cleaning alone is,
the practicability, right?
Yeah.
So laser.
I mean, if you're doing this as a factory production thing, maybe you just build those cleaning phases into your production process, and it's not that bad. But if you're doing it as a prototyping and design, you know, as an integrated sort of design, build, test cycle thing, you know, little things like that, little inconveniences that introduce delay into that cycle, I think are underappreciated, how important it is to try to get those out of the cycle. And this is something like software is something I work on a lot more, and there it's very well understood that the speed of the design, build, test cycle is critical. You know, you have to write some code, compile it, deploy it, see if it works. If it doesn't work, it never works. Then you fix it, and then you deploy it again, you check, you fix, and you do this 50 times every day. And making that cycle 10% faster means you get 10% more done.
Quite efficient.
You know, maybe it's even more than 10%, because if it takes too long to go around, well, then you go and have some coffee in between and you come back. And so people in the software industry put a lot of work into the efficiency of they're called IDEs, integrated development environments, that are the environment in which you develop and test software. And that's a very highly refined art in the software industry, to get those tools to be as clean and efficient as possible, because the engineers are very expensive and people understand how valuable their time is. And I think that it's interesting, like the laser cutter made me think about that in the context of mechanical design too, that you could really try to optimize that cycle. And you know, people obviously have talked about that. People in the car industry spent a lot of time developing, you know, CAD, CAM tools back in the early days of the computer industry, so that they could just see what a car is going to look like before they built one. Now, it used to be you would have some designs on paper, and you would have to actually build a physical model of the car. They would make it out of clay and paper, and
make a demo at first.
Make a model just to even see what it's going to look like. And then suddenly you can see it on the computer. And that's a huge advance. And suddenly cars got much more complicated. You know, the shapes and curves of a car became much more complicated once people could see them on the computer. But that's just the computer rendering. It doesn't really, like, you can't sit in it. You can't really feel what is it going to be like if you're in the car. You still have to actually make one. So, you know, but people understand that the efficiency of that cycle is crucial for innovation, right? If you can do that cycle faster than your competitor, you can build the product faster.
Yes, it makes the design viralized, right?
Right. It lets you get a physical version of the thing faster. And that's, I mean, I think people sometimes underestimate how important that is. That by making that cycle faster and cleaner and more convenient and more efficient, it drives your rate of innovation up. Because it just lowers the barriers to, well, let's just make one. And then, no, it's not right, because it's never going to be right the first time, so you fix it, and then you make another one. And wherever you can reduce the friction there, I think is valuable. And laser cutters are, for the things that they do, they're a great little bit of friction reduction in that space.
Yes, I agree with you. So one more question. Do you have any idea towards laser and innovative education? Because we know that you are developing AI with your partners.
Yeah, I think AI is, that's what I've been working on the last couple of years. Everyone in the software industry is working on AI now. It's sort of changed everything. And I think one question is just sort of philosophically, how do you think about developing an AI application? And the way I try to think about it is, what would I do if I were trying to teach a human to do this job? Because although AIs, they are not human, they're not really intelligent at that level yet. They are surprisingly intelligent, and they're getting more and more human-like. People, companies like DeepSeek and OpenAI and Anthropic, they are working very hard. They're literally spending billions of dollars every month to make these machines even more like people. So I think that over time, the approaches to training AIs and getting them to do what you want are going to look more and more like how you train humans to do what you want. Because the AIs are becoming more and more like humans.
Yes.
So, the project we're working on is an AI tutor for math, right? We want to make a thing that will teach students algebra, right? So how do we do that? Well, it turns out the way we do that is not very different from how, if we had a college graduate who is a smart person but doesn't know how to teach, how would you get them to be able to be a good teacher? So we're using the same sort of techniques on the AI as we would on a human. And I think one can imagine similar situations where, the way to think of what does the AI software do. Let's say you have your machine, it's set up, and you have this piece of metal, and you want to cut a certain shape out of it. Maybe you have a CAD file, with the shape. So if you have your engineer who knows how to use the machine, you would point to the metal and say, take this file and do it to this metal. And your engineer would then go, and they might spend an hour configuring the machine and setting all the parameters, right? They would look at the metal, they would see how thick it is, they would look stuff up in a table. All those, and then they would have the machine set up, and the machine would do its thing. All those things could be done by an AI instead. So instead of having your engineer and point to the metal, you would get your little robot over, or the machine would have a camera, and you would point to the metal and say, this piece of metal, I want you to cut it to this shape. And then the machine would figure out all of the complicated parameters and set them all up and cut it. And I don't think that there's right now any fundamental technical limitation why an AI couldn't do all those things. And quite possibly do them better than a human, because the AI can sort of memorize every single detail about this machine. It can know it better than any human could, because it's a machine, and machines are good at knowing other machines. So I can imagine in the future these things being much more automated. Like you give it a CAD file, you put the piece of metal in, and it cuts it. You just push go, because the machine figures out all of this complexity of how exactly to make that happen. And I think the fact that there are now robots very close, within a year or two maybe, of having robots that can come into your house, and you can see videos, some of them were faked, but some of them are real now, where the robot comes and it folds your clothes and puts them in your closet.
Yes.
Takes bags full of groceries, picks them all out, puts them in the right place. That's harder than running a laser cutter. Like the number of variables and complex parameters involved in doing a common household thing like that, much more open-ended kinds of difficulties that the robot has to overcome and that the AI has to understand and work through. So if they can do that, they can definitely run the machine too.
Yes, but any time, the robot...
It will take development.
Yes, the robotic folding machine can do the simple motion or simple movement, but laser cutter is much more different and complex.
It's different. I don't know if it's more complicated, but it's definitely different. And somebody will have to do a lot of work to, just like teaching a human to use the machine.
Yes.
Takes time.
Yes, just like to replace the work of engineer for training, right?
Yeah. But at some point, a CO2 laser cutter cutting acrylic is very close to that point, that you can just put the material in. You just have to set the power level and the speed. And that's pretty easy to remember, for a few different sizes, whatever. And then you push go and it works. I think the fiber lasers are farther away from that, but they could be very, pretty close to that.
Yes.
If one were to put work into the, AI controlling of it.
So back to the question: do you think do you think there's any relation between lasers and innovative education? In the education industry.
Yes, this is something I've talked about in some contexts where I think engineering education sometimes is very theoretical, and you end up with people who graduate as engineers who have never actually built anything. They studied all the formulas, and they can do these calculations or whatever, but they've never actually built anything.
Yes.
And partly that's because it's just too hard. To actually build something, it's not something you could do in a classroom, with 20 students or whatever. And so, good engineering education, you end up with internships where they go work for, a local company, and they actually get experience actually trying to work as an engineer. But that adds many years of training before they're actually practically able to make things. I don't know exactly how to define it, but there's a difference between a person who can write formulas on paper and somebody who can take their hands and go to a machine and make the machine actually work. And to go from being able to write formulas on paper to actually building something is a big step for a student. And so I've advocated to various people that what you should do is put a bunch of laser cutters in the classroom and immediately have the students start, like if they're mechanical design or something, have them try to actually build some three-dimensional structure out of parts that fit together. They have to have tabs and slots, and it has to not fall apart. It has to be, fit together, and they have to draw the CAD designs, take it to the machine, actually cut it out of acrylic, try to fit it together, and it will never fit together the first time, no matter how good the student is. But then they can, go back and figure out what's wrong. I sometimes help architecture students who need to make, when they're in their class on data, they have to make like a model of the building that they've designed. That's like their class project.
Wow.
And so many of them do this by laser cutting parts. And so I've helped a number of these students at our local university, and they come to me and they have these files, and I look at the file and it's, well, okay, but that part's going to fall apart because you've cut, you've cut in a way where it won't be one piece anymore. You'd think it's sort of obvious, but if you've never actually made anything, or this same line is cut 3 times in a row, and it's just going to burn the material. Lots of little things like that are the difference between a design that looks like it might work versus something that actually does work. You can physically make this out of real material and put it together, and it will actually fit together. That's a skill that they need to develop at some point. And a laser cutter is a great first place to introduce that step from theoretical design to actually making something. And if you had a classroom with, one laser cutter for every student, maybe just little ones, just a small cheap laser cutter, not one big fancy one, but a bunch of small cheap ones, then each student could sit by their machine and make, do this cycle, 5-minute turnaround of making the parts over and over again until they get it right. And then next time they're designing a CAD file, they'll think about it and they'll realize, oh, if I were to actually cut this like last time, it wouldn't work, or I should be careful with the lines not being duplicated. And,
yes, practice makes them better to understanding the difference between the theory and the in reality, right?
Yes, there's a saying that in theory there's no difference between theory and practice, but in practice there is.
Yes.
Theoretically, the design should work, but every time you try it, it never does.
Yes.
If you haven't ever made it before, it's not going to work. And you should just accept that. And so you want to make that cycle fast so you can then fix the things that didn't work.
Because there are so many other factors should be considered, like the materials, the structure.
It's just making something for real is just different than drawing it on paper.
Yeah, definitely.
And, that's something that I certainly became a lot better at, where, after I've been using the laser cutter for a few years and designing many little things and making them, I got to the point where I was much better than before at being able to design something on paper, and then maybe I have, an 80% chance that it will actually work first time instead of a 10% chance. So it's valuable to practice and develop the skill of being able to visualize and realize, oh, that's a little bit too thin. In this material, that part is just not going to be stiff enough. You don't need a lot of math for that. You need experience to know that that's not going to work.
It's really nice to have a talking with you, and we'll learn about something else, like your stories and your opinions towards lasers and your recent research.
Yes, well, I have many opinions and stories about many things, so keep going.